Welcome back to software engineering. This is the first and only video in the sixth module about support and maintenance. I kind of wanted to give you only one, maybe slightly longer video, just to kind of make up for the fact that we did the midterm this week. So far in the class, what we've done is we've talked about planning. So we've done requirements gathering, system analysis, and design, which are all kind of various steps along the path toward planning. We've also talked about how to actually implement pieces of software, how integration works, and all of that. We've also talked about all the different types of testing that we can do. So we talked about unit testing and smoke testing and package testing. We talked about integration testing, some kind of metrics that we can use to prioritize testing. And what we have kind of left off is the fact that if you think about something like Windows or Word or Excel, the vast majority of a system's life is spent outside of those phases. And so somebody at some point in time created the base code for Word, and now people have been using it for decades. And yes, some bugs have cropped up. Yes, some new features have been added. But the majority of that time has been spent somebody using Word, doing what Word was intended to be used to do. So after we've done all of these kind of lead up pieces of the development lifecycle, now we're in the sort of longest phase of development, which is continued support while a user is actually using the piece of software. So the first piece of this kind of puzzle is release management. And so release management is really based on the idea that you don't want to sort of give somebody the very first kind of beta version of your software system and then kind of go away and never update it again. All of the updates to that live piece of software are usually grouped into releases, and so they'll be grouped by maybe the bugs that the release fixes or the features that the release adds. And you can think about this much like Windows. So you have Windows Vista, Windows XP, Windows 7, Windows 8, and now Windows 10. And each of those has a slightly different look and feel. Each of those has different bugs that they fix based on their predecessors, so on and so forth. And so the important thing about this is there are really two kind of schools of thought around how release management should work. And we've talked about this several times in the class, but you can think about all of these things on a continuum. And so basically on one end of the continuum are projects or pieces of software that are really more like a project. And we're going to talk about this specifically in the software organization module. But project-based work is basically a client comes to you and requests this one-off piece of software. Potentially you'll be able to reuse the code, maybe not even, right? So potentially a restaurant or a bakery is coming to have you build a very, very niche kind of web application for them, whatever. That project-based work, when you get done with it, the user acceptance testing is done by the client on the client's data. And so what's going to usually happen is you're going to give them the download link, and they're going to go off and they're going to download the system and they're going to run it. Everything's going to be fine. Or you're going to host that system in something like Azure or AWS, and then you're going to give them login credentials. They're going to log into the system, do some testing, and then they're going to sign off and say that they're happy with the way that the system turned out. On the complete opposite side of the spectrum, you have things that are products. So you, again, can go back to Microsoft Office, for example. So you have Word and Excel and PowerPoint. Those end users are not employees of Microsoft, but the people who do user acceptance testing are members of Microsoft teams that are kind of stakeholders for those products. So there is some product manager somewhere for Office or for some subsystem of Office, and that person's team typically goes through user acceptance testing, making sure that the software team has actually implemented all of the requirements correctly, making sure that the non-functional and the functional requirements are met, all of that kind of stuff. So the difference here is that in product-based work, the user acceptance testing is done by the client, but the client is internal. The client is actually a organizational unit of the software organization. And for project-based work, that is an external client. So you're basically giving the client an installation, and the client goes and does some testing on their own data. So for product-based work, typically after UAT is done, that's when distribution actually happens. So once UAT is finalized, you have Microsoft Word 2016 in all of its pristine glory, and then you post it on the website, and now people, end users, can actually go out and download a copy and actually start using it. So within these schools of thought, there are really two kind of styles to perform release management, and they kind of vary in how much overhead they require. And by overhead, I mean how much kind of automated infrastructure you have to have in order to support these ways of living your life effectively. So the first of these is kind of the standard release way of performing release management. And what this means is that you have potentially a very long-standing kind of schedule of releases that will come out. And what will happen is typically these releases will not be required, and somebody can use, for example, Microsoft SQL Server 2008 for a very, very, very long time, even though Microsoft SQL Server 2012 and 2014 and 2016, so on and so forth, will come out subsequently, and they can upgrade to whichever of those versions they want as soon as the release becomes available. So this standard release model is usually used for enterprise level software, so something like SQL Server, something like Microsoft Exchange, these kind of business to business, not necessarily business to consumer applications. So rapid release is again, kind of the opposite side of the continuum from standard release. And what rapid release is trying to do is make the release management system as agile as all of the kind of planning and implementation components of the lifecycle. So rapid release is really focused on getting as few fixes out to the published kind of production code as fast as physically possible. And how this usually works is there's an automated process behind the scenes, and it kind of seamlessly rolls the latest and greatest code into whatever is published day over day, or half hour over half hour, or week over week, or whatever. And you can think about Hulu or Netflix or Roku even as examples of this. You can't necessarily say that you want to use Netflix version blah blah blah, and then you're never going to upgrade your Netflix. It just happens, and there's nothing that you can really do to stop it. So this is really great if you're doing business to consumer software, and the reason is because the user doesn't even have to understand that updates are happening. They just know that one day the button wasn't there, and then the next day a new shiny button was there and it did a bunch of cool stuff, and everybody was kind of happy. The bad parts, or the downside of this, is that it can go really, really wrong really, really quickly. So here I have an example where Roku originally had Spotify support in probably 2016, late 2016. And then in 2017, they released a breaking change for the application. And then month after month after month, the application became extremely unstable. You could use it sometimes, you couldn't other times. And then eventually, sometime in that year, they effectively put a splash screen up that said, hey, we're working on it, this is not available right now. And so you can only use Spotify on your smart TV if you were to use a Chromecast or something like that. So what can happen is you can accidentally release a breaking change, and then it becomes extremely difficult to back it out, largely because it can be buried in updates. And if your automated testing is not up to snuff, you could be releasing untested code into the wild very rapidly. And so obviously there can be downstream effects from any untested change that gets pushed into production by accident. So rapid release itself is most commonly used for software as a service products. So something like Roku or Netflix or Hulu. Something like Office 365, you can get periodic updates to Office 365 and largely be unaware that it's actually happening. The sort of operational downside to this is that it requires a lot of oversight, right? You don't necessarily want to get into a situation where you have no idea at what point in time the latest code will get deployed, and you want to be very sure that you understand what is actually in the code that's going to be deployed, because otherwise you can't really mitigate risk. You can't mitigate risk that you haven't computed, that you don't have quantified. So you can think of this, again, as kind of a continuum. And one of the things that I want you to take away from the class is that software engineering is largely an exercise in taxonomy. People can give names to something, and there's this very old saying that giving a name to something gives you power over it, and that's entirely fine. It allows us to have meaningful conversations about the components of software development and define best practices. But at the end of the day, right, what you're trying to do is you're trying to make software that works, and you're trying to make software that somebody is going to buy so that you can buy groceries. And so ultimately, all of this stuff is on a continuum, and in this case, you can think of something like the Windows operating system as a great example of something in the middle. So all the major releases, you can think of this again like Vista and XP and Windows 8 and whatever. Those are kind of standard release items. You have to go and you have to download, or you have to somehow use an updater or an installer to actually trigger that update. At the same time, they also have rapid release updates that come out maybe every other week or every week, and you largely have the ability to ignore these things. And I know people who ignore these for a very, very, very long time, and there are some that are marked critical, and you sort of are forced to accept them. But that is a great example of something that's kind of in the middle. You don't necessarily have to be either rapid release or standard. You could mix and match however you like. So going back to testing and kind of linking testing to aftermarket support, production defects are obviously going to be found once the product is live. So regardless of how good your testing is and how many people you have testing, how many automated tests you have, how good your overall process is, there's always going to be some bug that gets found by an end user. And ideally, what you're trying to do is just mitigate and make those bugs as less impactful as possible. So what will happen is these defects will get reported in some cases by an internal tester, and that's okay. That can happen pre-release, but sometimes it'll be reported by a user. And what really matters is how severe that issue is. If the user can't actually perform their job because of the defect, then that's obviously a very bad situation. If the defect is a color that's incorrect on a screen, maybe less urgent. So what really matters the most is how much pressure there is on the software organization to actually fix that defect. And as a kind of sort of like real world bit of information here, I have indicated that there are absolutely situations where the amount of money that a client spends in annual maintenance can push an otherwise ridiculous request to a very high priority request. So, for example, if you have a client who paid you $10 million a year for maintenance on an application they wanted to be green, and it is now suddenly blue, that $10 million will make it much more likely that you're willing to release an update to make the application green, even though that isn't actually causing them a lot of strife. It's just kind of a nuisance to them. So even though from a textbook perspective, the ability to do work, the system actually performing functional requirements, those are the kinds of things that are high severity. There could be non-severe issues that are escalated up because of non-software related things, because of issues in contracts or God knows what. And so that's also a thing to kind of be aware of as you go into industry. So severity, we were talking about before, you can't really mitigate risk if you haven't quantified it. So severity is quantified on a priority scale that is usually preceded by a P. So a P4 is a minor UI issue. It's something like grammatical issues with documentation or documentation issues. It is potentially you thought that there were going to be rounded corners on a button, but lo, the corners are sharp. These are the kinds of things that get logged. They could get fixed, but they're not a super urgent request from a client. A P3 is an issue with business logic, but you can easily get around it. So you don't necessarily have to go out of your way in order to do your job. You may be able to do something slightly differently, and then everything just kind of works out. So it's certainly not working as intended, but it's close enough that it doesn't actually hinder you from being productive. P2 is a bug, as we all kind of know and love them. So this is a priority issue around something like a business logic issue or a functional requirement that isn't being met with a non-trivial workaround. You have to kind of go out of your way in order to make sure that you can actually do your job. So this could be something like going to a completely different screen than the screen that you're used to. It could be performing multiple button clicks whenever you were really intended to only have one. It could be things like re-entering data multiple times, something like that. It's really, really annoying, but it isn't necessarily the end of the world. P1 issues, these are really high impact issues. So these can be things that include loss of data, data integrity issues. And the sort of telltale sign of these things is that there is not currently a known workaround. So until the issue is fixed, the client is just sort of out of luck. And if the bug exists in a non-critical business system, that's kind of okay. They can maybe wait until the bug is resolved. But the difference, the real quantifiable difference between a P1 and a P2 is that P2s typically have workarounds, P1s typically do not. And P0 is a critical failure, which means that multiple people cannot do their job inside of the application. So a P0 would be something like the entire application crashing, users not being able to log in, but it could also be something like a security vulnerability or something like that where users shouldn't be using the application because it's unsecured in some way. So P0 is the most critical, P4 is the least critical. The lower the number and the priority, the more likely that the software company is going to have to actually implement a fix and release a fix before the next major release. So depending on how severe these issues are, you can choose one of a multitude of different ways of fixing it. So if the defect itself is really, really problematic, you can obviously sort of release a fix to a specific file. So if you're using something like Java, you could fix the jar file and then send the updated jar. If you're working in .NET, you could fix the DLL and then update the DLL. But basically, each of these concepts is called either a hotfix or a patch. And the idea is you would be able to fix that issue and then patch that issue without taking the system down. And people who are currently using the system would be unaware that there was a change happening. It would just sort of happen under the table. And then the people who were not able to use functionality that was broken before would suddenly be able to use it. And the people who are not using broken functionality would not be interrupted. So if the defect is not severe enough for you to release an urgent fix, what you would typically do is put it in the product backlog, and then this whole process would circle back around. So you would have additional things in the product backlog. When you go to the next sprint planning meeting, the Scrum Master would go through and they would pull some of that backlog work onto the sprint, and potentially this defect that was found by a client would be wrapped up in that. And so how you do release management really determines how that integration from this point in the life cycle back to a previous point works. But you can kind of see that it's iterative. So all of this stuff becomes iterative, and over time, as your release goes through many releases or many patches, the hope is that the stability goes up and the bug count goes down. So hotfixes and patches, their sole goal in life is to push critical fixes into a production system. And so here, the word critical, again, kind of needs some quotes because critical is largely dependent on the eye of the beholder. So if the client is paying you a ton of money to maintain the system and they don't like the color of the splash screen and they think that's a critical fix, and you're contractually obligated to do whatever they tell you to do, essentially, you have to push that in a hotfix. The issue with hotfixes is that they are considered high-risk behavior, and the reason is you are taking code and you're rapidly pushing code into the code base, potentially with reduced testing effort. So usually major releases have a lot of testing. They have huge test case matrices. They have whole teams dedicated to testing them. These hotfixes usually have much fewer resources. They have fewer engineers writing the code. They have fewer testers testing it. Potentially, hotfixes only have automated testing. So if you have bugs in your automated tests, then obviously you could have additional issues. And so basically what you're doing is you are churning up the code, and you are never quite sure how safe anyone's code change is going to be. And we talked about in implementation how every time you check a new line of code in, unless it's a comment or a formatting issue that you're fixing, you could be introducing a potentially worse bug. So there are absolutely documented cases of people fixing a bug in one area of the system and then causing an even worse bug in a different area of the system. And all of this is kind of contingent on your architectural debt. So if your architectural debt is fairly low, your technical debt is fairly low, you can often get away with rapid hotfixes because you're not necessarily churning all of the system as you're trying to do these kind of minor fixes. So in terms of metrics, so we've talked a lot about code churn metrics, we've talked about volatility metrics and that kind of thing. Typically, if you're looking at a system that has undergone a lot of hotfixes, one of two things is happening. Either the code is growing up very, very rapidly, and so for a brand new software package right off the shelf, this is typically a very good thing. You're seeing a lot of development effort going into the product. So if you're looking at a very new open source system, for example, tons of check-ins and tons of releases is typically a good thing because that means that a lot of people are interested in maintaining the code, and the quality of the code probably is not negatively correlated to the amount of activity on the code. However, if you see a lot of hotfixes coming out of an established piece of code, or if you see a lot of hotfixes that reference the same sort of bugs, so you see a lot of regression bugs, patch 1 fixes a bug, patch 2 reintroduces the bug, and then patch 3 refixes the bug, that kind of stuff is typically associated with what's called excessive churn. So we talked about defect prediction a couple of videos ago, and the idea behind defect prediction is that you can use quantities about pieces of software to predict if that piece of software is likely to have a bug in the future. And one defect prediction metric is the amount of change that piece of code has undergone. So the more that a piece of code undergoes evolution or change, the more likely that piece of code is to have failures in it. And the more likely that piece of code is to have failures in it, the more likely it is that you're going to have additional churn that could potentially lead to additional bugs. And it's this sort of unrelenting cycle. So you can fall into either of these camps, and usually the big telltale sign is how long the piece of code has been around. If you are seeing excessive churn after a long period of relatively little work on the system, that's one thing. If you see a large amount of work or a large number of hotfixes on a piece of software for a very long period of time, that's typically a bad situation, and you're sort of in that cycle. So if you're looking at trying to improve your software release process, you can look at the number of hotfixes that happen between major releases over time. So if you're looking at the number of hotfixes that were released between release number 1 and release number 2, and suddenly that is 1/5 the number of hotfixes that were released between 2 and 3, you know that that is probably not a great sign in terms of either your testing or your release management process. It can actually be something as simple as not linking code to bugs. So you could have tons of hotfixes that are related to fixing a bug that's reintroduced, that's then refixed, that's reintroduced, that's refixed, and you don't operationally understand the nature of that bug because you don't have a good traceability between bug reports and the code that's actually fixing the bug. And then you're effectively getting the same regression bug over and over and over and over again, essentially every other release potentially. So the idea of a service pack is this kind of non-standard thing that usually indicates that there are a significant number of hotfixes, and instead of having to apply a whole bunch of hotfixes in series, you can apply a service pack that kind of rolls all of those hotfixes up. Many software companies, even particularly in the classical kind of standard release management process, call service packs and hotfixes the same thing. Truly, service packs have less requirements on them in terms of interruption of service. So service packs are expected usually to be a slightly larger, slightly more involved process. And because they're slightly larger and because they're slightly more involved, the software organization can expect that the client will want to test them more, particularly if they're for project-based systems. And usually this is a little bit of a time drain on the client. So even things like EWS, so Exchange Services for Microsoft, if you work in a very large law firm or an accounting firm or a major university, you're going to want to do some substantial testing of an EWS update prior to rolling it live, because you don't necessarily want everybody's email to just stop working on a Tuesday. So if you're releasing a service pack, you kind of have to provide documentation about what has changed and how the client can faithfully test that stuff to minimize their internal risk of adopting your new service pack. So in very large organizations, they typically have multiple environments that run your system. So you can usually chunk them into 3 buckets. The names are kind of a work in progress. These things are named all sorts of stuff. You can kind of see the progression of software at the client side. So in a development environment, what you're doing is you're running on the minimum possible specifications and the minimum possible viable product from the software vendor. And what you're trying to do is you're trying to rapidly test the latest and greatest code from the software vendor with whatever customizations you're doing. So there are plenty of integrations between email systems and business systems, integrations between Microsoft Office and business systems. All of that integration, all the customization, all that stuff is tested first in the development environment by dedicated testing engineers or in-house software engineers, so that people who are actually accountants and people who are not at all potentially tech savvy, those people are not wasting their time trying to do the testing that's going to find a bunch of kind of beta version bugs. The test environment is usually a full installation of the piece of software, and as close as possible, it mirrors what is in production. So this is an increasingly difficult thing, particularly for widely distributed systems. So if in production you work for a very, very large bank, and the production system is scattered around the globe on dozens of servers, you don't necessarily want to replicate that in test, but you want to replicate the experience in test. So you want to make sure that once you scale from test to production, the fact that it's distributed is not going to cause tons of problems in the production environment. In this environment, What you want to do is you want to make sure that business people, so the people in the business team, are actually testing, particularly items that they have already raised. So if they found a bug, you obviously want them to test to make sure that that bug is no longer there, but you also want them to perform effectively what's a smoke test to make sure that all of the core functionality is still working on the new version, and you're not going to have regression effects that are going to cripple the company once they promote from test to production. Then, in production, you have the currently stable release, and even though there are some issues in that release, hopefully you have workarounds that are fairly easy for each of those issues, and everybody kind of has a well understood way of doing their job, and everybody's kind of happy with it. So trying to step through what an update would actually look like, you could start with a kind of sanity check of the minimum viable product for a new system. We could call this version 0.1. It's essentially a beta test of a piece of software. Once you have done that sanity check, once you're kind of happy that all of your customizations are going to work, and that once you try to communicate from this system to your email server, the email server is not going to explode, you can promote that to firm-wide UAT, and now people on the what we've been referring to as the business team are actually using the software system even in its beta version, and then you're going to collect data from them. So they're going to give you all the bugs they find, they're going to give you all the features they request, whatever, and that's going to potentially get sent to the software vendor, and where you as a software engineer are going to be made aware of it in a Scrum meeting. After UAT is done, the firm would adopt the release, and so this part is actually in the previous software lifecycle phase, so this is part of testing. So once UAT is done, they would sign the piece of paper that says you've done your job, and then they would install, or they would start using the production instance of that piece of software. The problem is that eventually they'll have some sort of issue, and then we're going to call this thing bug report number 1. So maybe it's the first day, maybe it's the second day, maybe it's the 831st day after adopting the version 1 or 0.1 in this case release. Somebody at the firm is going to find an issue, and you're going to hope that that issue is going to be fairly minimal, because if you're testing, then it's not going to be a big deal. But what happens if this is bug report 1? If a user's last name begins with the letter T, when they try to log in, the application throws an unhandled exception and crashes. This is obviously not a P4. This is going to be something like a P0. This is a very common letter to have at the beginning of your last name, and this obviously is a thing that needs to be fixed. So we would go back, and we would go to the development environment, and we would apply version 0.1.1. This is a service pack in this case. Maybe it has additional bugs that have been fixed. They would test all of those fixes in the service pack on the development environment, make sure that all the customizations work. Again, make sure that your email server isn't going to crash when it gets communication from the system. Then they would promote that right back to the UAT environment. UAT would happen on this version from the same business team. Hopefully you're getting the same people to test over and over, because they're more sort of knowledgeable about the system, and as soon as they have given it the green light, it actually fixes our bug report 1, and it fixes all the other issues that they've raised, and it doesn't cause core functionality to cease working, so you still have some smoke testing component here. They will promote that to production, and now suddenly bug report 1 is no longer there in production, and everybody's happy, particularly if your name begins with a T. So this kind of idea works very well. It's very intuitive, particularly if everything is a bug request. The waters start getting muddy around feature requests. So feature requests are effectively a defect that is found with requirements gathering. So either you missed a requirement at the beginning, or the requirement didn't exist yet, and suddenly now the users of the system want an additional piece of functionality or an additional feature added to the system. So a major source of ambiguity for software companies and for users of software is what is the difference between a feature request and what is actually a bug. So there are dozens, if not hundreds, of papers and white papers written about this idea. And it seems silly at first, but it's kind of important that you as a software organization have a fairly rigid definition of what this means, so that you can communicate that definition to the users, and they can appropriately sort of tell you what they're trying to look for. If it's a critical bug they're trying to get fixed, or if it's additional functionality that they're requesting. And so the textbook definition of this is really missing functionality. So if it's missing functionality that was not originally scoped, so if there is not an existing requirement that this functionality be present, and they're adding a requirement, so instead of going back to implementation, this iteration is going back to requirements gathering, that is a feature request. The waters get even more muddy when you have a really high dollar support or maintenance contract with a client, and they are a very good client and they faithfully pay their bills, and suddenly they very, very deeply want a feature added. You can sometimes kind of squint really hard and make that into a bug. The reason it's important is because traditionally hotfixes and patches do not contain features. And this is for the exact same reason that hotfixes are a sort of high-risk behavior. If you have a hotfix, you have a patch, you typically don't have a full engineering team, you typically don't have a full testing team, and trying to put out a new feature in that environment is not necessarily what you want to do. However, again, money talks, and potentially you have a client that is a good enough client and the feature is well enough understood that you're willing to take on that risk for the potential payoff. And so software engineering is a business, and ultimately you have to kind of make these decisions based on the amount you're going to get returned on whatever investment you're putting into the release. So one thing that we haven't talked about as much in the class is that you have very likely experienced this situation where you've written a code, particularly for a class like Java or Python, that worked fine on your machine, and then when you put it on LinProg and someone tried to grade the assignment on LinProg, suddenly there were issues. And this happens very, very frequently in at-scale software, because basically Microsoft is writing Word, and it's certainly testing Word on many different configurations of many different processors, many different versions of the operating system, but they can't necessarily hit all of them. And they certainly don't have access to all of the other applications that you're running at the exact same time. So it is virtually impossible to test a piece of software using every possible combination of operating system flags, so registry keys, and networking configurations, and every other piece of related software. So not only would they have to test Word, but they would also have to test every version of Outlook with that version of Word, because you might be using integration between those two pieces of software. You might be using open source software that they've never even heard of before. And so configuration bugs are all the bugs that exist in this kind of interstitial space that is very hard to understand from an organization's point of view how they actually happen. So these configuration bugs bring up the true reason for what's often referred to as tech support. So you have a whole bunch of people that are sitting around and they get paid to take phone calls or field emails, and those emails will have crazy things in them, and it's the job of the technical support team to triage all of the feature requests and all the bug reports and all of the issues into three kind of buckets. So actual bugs that happen and need to be fixed by the development team, documentable configuration issues, so if you're working on a 32-bit machine, this application won't work kind of stuff, or feature requests that need to go to management, or they need to go to an architect, or they need to go to a product manager for prioritization and then scheduling in a sprint, in an upcoming sprint, or an upcoming release. So the job of tech support, this is largely becoming, or has become, a little bit of a meme-ish job. You kind of sit around in a phone bank and you roll your eyes a lot, and then you ask somebody to unplug their computer and plug their computer back in. But tech support is a critical component of this entire life cycle, because without these people staffing this triage center, you, as an engineer, have to go through all of these things. And typically, spending an engineer's time doing research on configuration issues is not very well received. It doesn't actually help you all that much, because the education level required to figure out configuration issues is significantly lower than actually implementing a piece of software. So as you can see, this entire process is extremely iterative. So basically at the end of the life cycle of a piece of software, you're getting a whole bunch of requests into tech support. Those people are triaging them, and some things are going all the way back to analysis, some things are going back to testing, some things are going back to implementation. And through that process, those new bugs or new features or new pieces of code filter down to release management. They get released into the wild, and then the whole thing kind of starts over again. And so it's this huge loop. And so even though your system could have been live for 10 years, there will always be the 3-sentence email that is for a feature request that somebody in support has to send to a business analyst or somebody in the management team, and that person will have to figure out how to tease out exactly what the requirements of that feature are, make a specification, and figure out how to schedule and implement and test that piece of code. And so typically prioritization in that sense happens based on how much benefit the team thinks general users will get from that new feature. If it's a lot, then typically the company will kind of rush that to the front. If it's a request that doesn't have a lot of traction, not a lot of people want the request, it might sit around for a very long period of time. And so ultimately, it is the management's decision, so people who have control of the company, it's their decision on when to stop the cycle. Typically that can be because you want to sunset the process, or that's just because everything is kind of low return on investment, right? If you're getting the same 3 requests from 5,000 users, and when you implement those 3 requests, the requests stop, you don't really have a whole lot of additional work, then you can obviously move your engineers to a different project and kind of let that project be on its own and do its own thing. It's kind of a self-perpetuating piece of software at that point. So sunsetting is kind of the legitimate end of the process. It's the end of the line for a piece of software. And this is a process that takes a lot of different shapes. And basically, if the core functionality of a piece of software is outdated, if the framework that it's built on is deprecated, so you can't actually update it anymore, or if the purpose of the piece of software is no longer relevant. So if you have a project for a specific client, and the specific client goes out of business, they don't have to have the piece of software anymore, so you can decommission it. And so at the end of sunsetting, what you have is you have maybe legacy code, and you can certainly keep that in a repository like GitHub or something like that, but you no longer have that code running anywhere and nobody's actually using it. And so you can think of this sort of like massively online games. There was a really popular one that got sunset several years ago at this point. And basically that when that happens, nobody can play the game anymore. It just sort of shut off. So sunsetting can certainly happen when there's no additional users on it, but like I said, it comes in a lot of different shapes and sizes and varieties. And so sunsetting to some companies actually means that no further changes will be made to the code base. So users can continue to use the software, but if they find a bug, that bug will not be fixed. And they will be sort of forced to update to the latest and greatest version of the new piece of software. You can think about this as Microsoft Windows XP. There was a huge email out to people who were still running XP that in X number of years they would no longer be able to get updates on their XP systems, and the reason is because that piece of code was being sunset. So to tie kind of all of this stuff together, the point at which you've made the decision to go on-premise or through a hosted platform like Azure or AWS comes back in this very last step. So if you are working with a client and that client has an on-premises version of the software, it's very, very, very difficult to actually go and physically shut their server off. And that would probably not even be a legal thing that you could do. So these on-premise systems can largely exist without support for a very long time unless a critical issue is found. The interesting thing about this is the closer to sunsetting a system gets, the longer the system has been alive. And so if the software development lifecycle went correctly and the software got more stable and more stable over time, it's less likely that an older piece of software would need support. And so you can run into situations where you can be running a very old piece of software on premise, and the fact that you don't have support doesn't actually impact you all that much. At the same time, if you chose to do a hosted only solution, all you have to do is go into the AWS or the Azure console and flip a switch and turn the service off. And then suddenly all of the people who are no longer paying for support or maintenance, they cannot access the piece of software. So this is kind of the final point in the lifecycle where you see choices that you make previously in the process or in the lifecycle can come back to play a role in something that's happening now. So all of the kind of architectural concepts that we put around choosing on-premise versus a hosted solution come to a head here when if you have an on-premise solution, typically it's impossible to truly sunset the piece of software. Usually what you're actually doing is just saying, hey, we're not going to support it anymore, and kind of throwing your hands up. So that ends the sort of software lifecycle part of the class. So this kind of goes through the entire process from an idea, collecting a whole bunch of requirements, up through designing the piece of software, implementing the piece of software, testing the piece of software, and then supporting the piece of software potentially for decades after you've released it into the wild. In the next couple of weeks, what we're going to do is we're going to talk about research in software engineering. We're going to talk about organizational structures and kind of the accoutrement that comes at the end of the semester. And so hopefully this first maybe 2/3 of the semester kind of give you all the tools that you need in order to be successful in the group project, because at this point you've seen all of the individual components of the lifecycle. But as always, if you have questions, comments, concerns, please let me know, and I'm happy to answer those. Thank you very much for tuning in, and I will see you next time.